So let's talk about lab from, which seems like Friday, because today seems like Monday, but lab from Tuesday. So here's the whole idea of this, is that every situation on this lab is going to deal with this concept. Force applied plus force opposing plus force net. Okay? That's the idea. And so literally, either you accelerate and the net force is either a positive or negative value, or the constant velocity and your net force is zero. Okay? So one of the things I want you to get out of your minds right now is the idea that just because something is moving at a constant velocity, there aren't any forces acting on it. Okay? No. The only way you can move at a constant velocity without any forces acting on it is if you were like in deep space, okay? Where your inertia will just keep you moving. Or you completely eliminate friction, right? Realistically, you're going to have a force to keep it moving because there's always going to be friction. So here's what I want you to see, is that when you guys took that scale, and the whole key to this is that you made that mass accelerate upward, okay? And in this system, we're defining up as being positive and down as being a negative value. So you wanted this force net to be some positive value. But you have to remember that what you were reading on the scale, okay, what that scale was giving you was your applied force. So let's say that was, I don't know, 7.9 newtons, okay, whatever it was. I'm just going to make up a number. Let's say it's 7.9 newtons. Your opposing force is what you have to pay off to the gravity mafia, okay? Which in this case, because it's a 500-gram mass, is going to be negative 4.9 newtons. So that leaves you a net force of 3 newtons, okay? Topher goes to the lunchroom. He buys the watch for $4.90. He sells it for $7.90. He makes $3, okay? So, again, I emphasize this. You are measuring the applied force. So, and also get out of your minds that just because you have a positive net force, that means that you're moving upward. The direction of the net force is no reflection at all on the direction that you're moving. All you know is that you have a positive net force. I could have a positive net force with a negative velocity and be slowing down. I could have a positive net force with a positive velocity and be speeding up. So the sign of your net force does not tell you a direction that you're moving. It just tells you the direction of the force. Okay? That's all it tells you. No matching today? I don't know if I can handle this. I'm not used to looking up and seeing like, different images. I don't know if I can handle it. Oh, they do? Yeah, kind of. Oh, I can see that. That's legit. Okay. Now, so let's talk about the difference between question 10 and question 11. So on question 10, here's this elevator, right? And if you're not sure what's going on, draw a picture. So this elevator is moving upwards. So is there going to be gravity involved? Yes. So you're going to have some gravitational force acting down. What are the two most important words on question number 10? Constant velocity. Okay? Two most important words. Therefore, the forces add up to zero. So if you know what your gravitational force is, which you're going to find by taking mass times your gravitational acceleration, make that a negative value, then the force in the cable is going to be acting upward. That's going to be a positive value. Make the two values add up. Now, think through your answer to number 11. Okay, just think through this. So here's this elevator. It's moving, right? Constant velocity, puts a certain amount of force. Now, not only do we want to make the elevator move, we want it to speed up. Okay, we want it to have a positive acceleration. So think about this. You're driving your car at 40 miles an hour. Speed limit changes to 55. You're going to accelerate. What are you going to do with the gas pedal? Yeah, you're going to push down, right? you're going to apply more force because you want this thing to accelerate. Same thing is going to happen with this elevator. You want this elevator to accelerate upward. You still have to overcome gravity. So here's what you cannot do on number 11. You cannot just take the 534 times 1.3 and say, oh, here's my answer, okay? All that is finding you is the net force, okay? You still have to pay off the gravity mafia. So your answer to number 11 has to be bigger than your answer to number 10. Because not only are you lifting the elevator, you're making it accelerate and go faster. So that's going to take even more force, okay? So if you want to look at this in terms of your chart, and I beg of you to remember that your net force, and only your net force, equals mass times acceleration. So you do need to take the 534 times 1.3. Take 534 times 1.3 meters per second squared. Boom, there's your net force, okay? What you're looking for is your applied force. You can find your opposing force because that's that same answer that you found up there on number 9. So if you want to make this positive, this is some negative value. If you want to do the algebra, you can look at it from vectors. I don't care. Okay? There's any number of ways that you can work this problem. But just realize your answer to number 11 has to be bigger than your answer to number 10. Now, on number 12, here's your scenario. If you're an engineer, you always plan for a worst case scenario. So you're designing this elevator. And you sit there and think, okay, what's a worst case scenario? Okay, worst case scenario is that my elevator ends up in a hotel and it's invaded by a bunch of fraternity brothers who want to see how many they can cram inside the elevator. So, okay, worst case scenario. That they're going to put 20 fraternity guys inside the elevator, average mass of 75 kilograms, and every string, cable, chain, whatever, has a breaking point. So, and that's one of the things that you kind of need to know. So if I take this, even this string, right, and I pull on it, at some point it's going to snap. So it can only withstand so much strength before it snaps. So you're an engineer and you go, okay, here's the maximum strength that this cable can withstand without it snapping. Okay? Worst case scenario. That if you're an engineer, you always plan for worst case scenario. You hope for the best, but you plan for the worst. Okay? That's kind of your mantra as an engineer. Hope for the best, plan for the worst. So, if you look at what's happening here, first off, you need to find the total mass that has to be accelerated. You have the people that are inside plus the elevator itself. Okay? So you need that number. So you need the total mass that's going to be accelerated, which is like 2,000 kilograms. Okay? So that's the total mass that you have to accelerate. So, what you want to look at, and I tell you this, okay? Oddly enough, that applied force is that upward force of 2.96 times 10 to the 4th. That's your applied force going up. Then ask yourself, is there any force opposing this? There's the gravity mafia, especially if this is a hotel like in Chicago. Okay, you're the mafia then. So you're going to have some downward force that's working against that. The difference between those two is your net force. Divide that by the mass. There's your acceleration. So your acceleration on number 12 should be between like 4 and 6 meters per second squared. Okay? What? Are we okay?
Yeah.
Okay. On number 13, here's your helicopter. It's going to take off. So think this through. Does your answer to number 13 have to be bigger or smaller than the weight of the helicopter? Bigger.
Bigger.
Okay? Your answer has to be bigger than the weight of the helicopter. Not the mass.
Oh, duh,
Okay?
yeah.
Bigger than the weight of the helicopter. So take that mass multiplied by 9.8 meters per second squared, okay? That's your opposing force. So if you think about this, your answer to number, how you work 13 is the exact same way you work number 11. Okay, it's the exact same process. This is why I said these are known as elevator problems. Okay, so anytime you want to accelerate something upward, at a minimum you have to overcome the gravitational pull acting on it, plus the additional force it takes to make it accelerate. Almost all of your answers on number 14, almost all of them, should be something times 10 to the third. Your applied force on number 15 should be something times 10 to the fourth. Okay, pretty big number. Now, let's talk about the Atwood machine problem.
This one got me good. It's 10 to the fourth, the force applied. Do 10.
Okay, so you've got 220 on one side, right? And 200 on the other one. Which way is it going to go?
The bigger one.
Okay, which one?
220 up?
The 220 is going to go? The 200 is going to go up, right? Cool with this? And here's the beauty of physics, is that I could have walked in the very first day and given you that diagram. And so what's going to happen? Oh, 220 is going to go down, the 200 is going to go up. Okay, why? Oh, more force on that side. You all intuitively understand physics. This is the beauty of it, okay? We just have to look at the math. Now, here's the deal. Do not make this complicated. Make the 220 the applied force. Take 220, divide it by 1,000, get it into kilograms, multiply it by 9.8. Get the downward force acting on this, and that's like 2.16 newtons about, okay? So in round numbers, I got a 2.1 newton force pulling down on the bigger side. I got a 1.96 newton force pulling down on the 200 side, okay? That's it. 2.16 to 1.96. It's like a tug of war, okay? You okay? You're like, ah!
I accidentally bumped her and then she.
It was like right here in my ribcage.
Oh my gosh.
Gosh.
I went like this on accident. That is the case.
It's actually why we don't
It's not like I went like
Okay, all right.
You can put like a trainer like a mess.
I think I would cry with you and Dwight said this.
Okay, so think of this as a tug of war, okay? Nick and Dime are pulling on a rope. Dime's pulling at 2.16 newtons. Nick is pulling at 1.96 newtons. Who's going to win? Dime? By how much? About 0.2 newtons, right?
Newtons. Yep.
Okay, that's about how much he's going to win by. Okay, so what we're saying is that conceptually, it's like we're going to take a 0.2 newton force and we're going to take that one force and we're going to make it accelerate 420 grams. Conceptually, that's what's going to happen. So if you look at F equals ma, we're going to take that net force and that's what's going to make the whole thing accelerate, okay? So this is why at the end of the day, when you calculate that theoretical acceleration, you have to divide by the total mass of the system. And that's that first question down below. It says, why do you have to divide by the total mass? It's because anything that has mass has inertia. So when you let go of those, both of those masses will resist a change in the velocity. So it's like having one single force acting on that combined system. Okay? That's why you have to divide by the total mass. Because both have mass, both have inertia, both resist a change in velocity. Now, when you get to question number 2 on the bottom of page 3, So here's what I'm asking. If you look at how you calculate this applied force, okay, this is what I want you to be able to think through, okay? So one of the key successes in life is being able to think through complex problems. Figure out the algorithm, figure out the thought process. So how did you calculate the value of that applied force? What did you do? Look up above. How did you get the applied force? No, what did you do?
You take the mass of the bigger one
Times?
times gravity's acceleration.
Okay? So you took 0.22 kilograms times g. Did you have to know what this mass is over here? Did that have any bearing on that calculation? No. The fact that they were made out of brass didn't matter. Okay? They could have been painted pink. They could have had horizontal stripes, diamond pattern. Doesn't make any difference, okay? Just saying. Khakis, whatever. So here's the point. Look at what is a factor. The only factor that determines that applied force is the mass. This has nothing to do with the value of the applied force. Okay? Now, here's the next question. Now we're going to talk about net force. So here's what I want you to think through. Gravity's going to be pulling down on this no matter what. The question is do you have to take your little brother with you when you go out on a date? Okay, that's the $1 million question, okay? Now, I'm going to pick on Topher because I taught both of his older sisters, okay? So, both of his older sisters, they're excited, they're going out on a date. His dad says, hey, you got to take along Topher. And cute as a button as he is, they're going to be like, really? Okay, we got to take along Topher. Okay, so he's going to be like this opposing force, so they're not going to be able to accelerate as quickly. So, I'm just telling you, it's true. Don't act like it's not. Okay? Well, actually, you might have made them go faster. So, but let's go with him being an opposing force. So, Topher, come on, let's go, let's go, let's go. So, anyway, so now, assuming that Topher is acting as an opposing force as they go out, situation number 2, they go, no, you don't have to take Topher. So at that point, you lose the opposing force, okay? You lose what's dragging you down. So what's going to happen to your ability to accelerate? It's going to go up. Now, there's an interesting thing that happens mathematically. Once you sever, if you severed this string, not only would you have a bigger net force, because you don't have an applied force, you would also be dividing that bigger net force by a smaller mass, because now you only have to accelerate this mass, you don't have to accelerate that one with it, okay? So keep that in mind. All right, any questions on that lab? What, Bubba?
For the force applied on the force applied problems on those,
What?
Can you
What
be
question?
any more vague?
like, I don't know how to explain it. Like, for the 200 grams, 220 grams,
Yeah.
220 grams is a force applied, but like, would that be negative force applied? No?
Don't make it complicated.
Yes.
He says on the lab,
Don't make it
make the bigger one your applied force.
Yeah, I know, but shouldn't that be a negative force?
No, just make that positive.
No,
I don't
He
care
said
which
that
one.
yesterday. Oh, you weren't here yesterday, were
Just
you?
make this positive,
Oh.
make that one
He said that
negative.
yesterday.
Okay.
Even
cool.
Wait, you weren't here yesterday?
There's a smaller
Was
What?
I not here yesterday?
Larger with the asterisk.
I don't know, was I?
You just want just to explain like within the answers
That's
as well?
yesterday.
Huh?
I was
Everyone here.
surprised.
On the end of each question.
I didn't realize it until afterwards.
Yeah.
Okay, my
Do you have a hairbrush,
Jesus,
Ella?
why did you yell at me?
I don't even have to yell at you.
You got mad.
I said I was confused. I
Yeah.
was going to ask.
Oh,
Yeah,
God.
that's,
Nice.
Eli.
Be nice.
Oh,
Eli.
that's cute.
generally, when in doubt, I always.
I
want you to
designed
explain your
that.
answers.
I figured, yeah.
Yeah, and so I didn't really
Wait,
want
Mason.
to be honest, I ran out of room when I had that whole thing typed out,
We are.
and I had to reformat the whole thing, so that's why I put an asterisk at the end of it. Okay, anything else?
No.
Going once, going twice, so get those.
Can I still do that one throw play though?
Okay. So, here's the setup. I've got two pulleys, okay? I've got a 500 gram mass tied on that side, and I have a 500 gram mass tied on this side. In between the two, I have a Newton scale spring, okay? So I've got one end tied to one end and the other one attached to the other. A 500 gram mass on each side, 0.5 kilograms, right? So here's the $1 million question. What's going to be the reading on the scale? So there's three options. Option number one, the reading on the scale is 0. The system is in equilibrium. It's being pulled equally. The reading on the scale is just going to be 0. That's option A. Option B is going to be 4.9 newtons because a 500 gram mass by itself is just 4.9 newtons, so it's going to be 4.9. Option C is going to be 9.8 newtons because it's pulled in both directions with a force of 4.9 newtons. Okay? So those are your three options. It's either 0, 4.9, or 9.8. Those are your three options.
It's a
So
Newton
how
scale?
many? Huh?
You said it's a Newton scale.
Yeah, it's a Newton scale.
Okay.
So those are your options. So when I lift this up, those are your three options. So how many vote the reading on the scale is just going to be 0? 1, 2, 3, 4, 5, 6. Okay? About 6 of you are on the 0 train. What about the 4.9 train?
What's the other option again?
9.8.
Mm,
Nobody's on the 4.9 train.
I think.
Just do it. So
Yes.
Oh wait, yes, I think so, but maybe not.
Definitely.
I'll do it.
So, are you on the 4.9 train?
No.
But
So
think,
3 are on the 4.9 train. What about the 9.8 train?
Oh yeah.
please say I'm right.
Okay. So, it was 0, 4.9, 9.8.
You had a 30%
Okay.
chance.
Drum roll.
So, the smallest number of people that were hesitant were on the 4.9 train. So, were you emphatic about the 9.8?
I was emphatic.
Why are you emphatic about the 9.8?
Well, because
Dang it,
looking
is
at
he
it,
right?
it's like staying up in the
I hope he's
Yeah.
wrong.
at the same spot, and gravity is acting on it, but it's staying at the same spot, so it has to counteract gravity. So it's gotta be 9.8.
Okay.
That's my theory.
I'm 50-50 on that one.
So now, so you can make the argument that it might be. So for those of you that were on the 0 train, why were you on the 0 train?
Because my brain said.
My brain thought it read net force.
It's applied force.
Opposite direction.
It's
It's going in opposite directions.
It is
It has
applied
to be
to
9.8.
Yeah, it's
Yeah.
a measuring
Okay,
applied.
so it's, yeah.
Okay, so you're saying it's gonna be in 0 because it's in equilibrium, it's pulled in both directions. Okay. Topher,
One is pulling 4.9 this way, one's pulling 4.9 that way, but it only has one hook, so it's not.
I agree.
I like it.
hey,
Both sides are applied force, so it adds up to 9.8.
so since both have an applied force of
That's basically what I
4.9, it's
said.
gonna double to get 9.8.
It's 4.9, right? Can you tell us?
I will.
When?
9.8, you changed to 9.8.
4.9.
Why are you on the no. Hold on. Why are you on the 4.9 train?
Because I like that option. I don't know. There's two forces applying. There's two of them. I don't know. I feel like it has to do with like the acceleration and like the mass.
It's not
I know it's not accelerating, so Actually,
Let me ask you this,
I don't know.
okay? Let me ask you this. Quit playing for my magnet.
4.9?
So what if, let me riddle me this.
I'm good at riddles.
What if I just held this end of this, so there's the hook on this end, right? What if I just held this and took the weight off of this side?
That's taking away.
It would be 4.9.
Yeah.
Now it's 9.8.
Now it's
9.8 on that side.
Let's go.
No, it's they didn't change it. Oh, okay.
9.8.
How do we know?
They're at 4.9.
It's 4.9.
Yay!
Hey, you shouldn't have changed. It's 4.9.
Oh my god!
Okay? Now, here's the reason why.
Yeah.
Okay? If you think
My
about it,
intuition.
this side over here is just, if I take this weight off, you'll notice that that reading on the scale does not change. It's 4.9. I put that back, it stays at 4.9. Okay? Stays at 4.9. Because basically what this side is doing, that side over there is just basically, if you think about it, it's just acting as an anchor. Okay? So that's there to hold that in place. So what this side is doing is just measuring the force that's actually pulling on this side to make that measure 4.9 newtons. Now, what if I put what if I put like another 20 gram over there and kept 500 grams here? Then what would it begin to do?
4.9.
Go increase.
Yeah, it would begin to accelerate, right?
Oh, wait,
So
yeah.
then it would begin to accelerate in that direction. But as long as I have equal masses on both sides, all this is doing is just acting as an anchor to hold that in place. And so that's why it reads 4.9 newtons. Okay? I'm lying? Okay.
Wow, we're so smart.
Okay. All right. So now, what's the light? So shut that down. Let's go to the back.
Save less. That's scary.
Oh my gosh, front back, front back.
Front back, front back.
Front back, why? Paper's so thick.
I just don't get it. Do you feel how thick this paper is? Yeah, it's really thick. What is your voice? Hurry, before you decide. 18.
No, there's way more than 18. There's 18
A
in the second
calamity
part.
of carts and things that go bump in the night.
There's like 30 questions.
There's like a thing that.
There's like 30 questions. Yeah, there's like 30. Oh my god.
Even though it's big and it's.
How much is your watch, Sam?
I don't know, my brother got it.
Oh,
I
that's
forget
very
you have
fancy.
siblings. I hate Sam.
My brother's nice.
Do you need food?
It's very materialistic.
I didn't eat any of my lunch today.
Why is it so quiet?
I'll sing.
Okay, go ahead. Why are you doing it, Kaylee? You said you would.
Okay. Start up your camera.
Oh yeah.
Really gotta call me from Hannah.
There we go.
Okay. So this is going to be like the third lab that we've got. And again, it's all about force net equals force applied plus force opposing. So here's what you're going to do. I'll show you that. Watch it. I'll show you the setup in just a second, but I want to kind of get through the theory part. So what you're going to do is you're going to take a cart, and you're going to use a similar pulley system that I just used. And you're going to take a string, and it's going to be, you're going to put a tiny little 10-gram mass on the end of the string. And that's going to go up, and it's going to be attached to a cart. And the cart itself is going to have a 500-gram mass, and it's also going to have a 20-gram mass. So visualize this. I have a 10-gram mass here. I got a 20, a 500, and the cart itself. Now, pretend that the cart isn't attached, okay? Don't focus on the cart. The cart is not part of the story at this point. It will be part of the story. It's just not part of the story right now. Let's just say that you have a 10-gram mass, and I want to know how much force is acting, caused by gravity, on that 10-gram mass. So Jack Ring, what am I going to do? I wanna find the downward pull on a 10-gram mass. What are you gonna do?
We'll multiply that mass times the acceleration of gravity.
Am I gonna leave it as 10 grams?
No.
No. What are you gonna do?
Convert it to kilograms.
By dividing by 1,000. So, Jacqueline, you have a calculator up there?
I do.
I need you to take 10 and divide that by 1,000. Then multiply that by 9.8.
Oops, I could divide again. I got 0.098.
Fantastic. Okay. So when I have that 10-gram mass hooked up and lifted, gravity is pulling down with a force of 0.098 newtons. True? Everybody cool with this? Now, don't worry about making that negative, just get the number, okay? Just get the number. So here's the story. If you look at force applied, force opposing, force net, okay? When that 10-gram mass is just hanging there, what's the value of the net force?
0.
0, right? That's not accelerating, true? So, what's the relationship between the applied force and the opposing force then? They're equal and
Opposite.
okay? Now, so when that 10-gram mass is just hanging there is an upward force of 0.098 newtons, which is like this tug of war, okay? Gravity is pulling it down, and the string is going, nope, I'm gonna keep you from falling, okay? What if I just cut the string? Okay? What if I just cut the string? If I just cut the string, what's the net force acting on the 10-gram mass? It's still going to be 0.098 newtons, right? If I just cut the string, the net force acting on the system is now going to be 0.098 newtons. To get the acceleration, what would I divide that 0.098 newtons? What would I use for the mass in F equals ma? If I just cut the string.
The
The
bigger
weight,
one,
right?
or the one that's not.
No. If I just cut the string,
The mass of
what's
the
the
weight.
mass of 10 grams? 0.010 kilograms, right?
Okay, yeah.
So here's my
Like you
point.
cut it.
If I take 0.098 newtons and divide that by 0.01 kilograms, oddly enough, I'm going to get 0.8 meters per second squared, right? If I just cut the string, a force of 0.098 newtons acts on a 10-gram mass, I get an acceleration of 9.8 meters per second squared. Everybody cool with that? Okay? However, we're going to drag that cart up above. Now, what we're going to assume is that this is a frictionless surface. Okay, that's going to make the math easier. Okay, we're going to assume that there's no friction between that cart and the track. Okay, so once I realize that I'm going to drag that mass, I'm going to drag that with it. Is my acceleration going to be bigger or smaller than 9.8 meters per second squared?
Smaller.
Smaller, why? Explain it in terms of F equals ma. But what's the same?
The
The force?
force
It's the
is
same net force
different.
of 0.098 newtons, right?
Yeah,
But what's happened to the mass?
it's increased.
It's increased, so therefore my acceleration should decrease. Okay? So my acceleration should be a lot less, because now I got to drag this whole cart with it. It's like, oh, okay. It's not going to accelerate as quickly. Okay? Cool with that?
Yes.
Got it. Now, what if I take the 20-gram mass that's up there, and I put that on the end of the string, and I take the 10-gram mass and put that up there? So I swap it out. I take the 10 gram, put that up on the cart. I take the 20 gram, I put that
And then just fall
on the end of
down.
the string. What's that going to do to the value of my applied force?
Increase it.
Increase, because now I have more stuff hanging on the end of it,
Yeah.
right?
Yeah,
But what's going to happen to the total mass of the system?
it'll yeah, because of
It's going to be the
yeah.
same. Why? Yeah, I took the 10 gram, I put it up there, took the 20 gram, put that on the end, right? So the total mass is the same. But what should happen to my acceleration? My acceleration should go increase. Because if you look at F equals ma, I'm going to have a bigger force acting on the same mass. I should get a bigger acceleration. Got that visual? Okay, so stop the camera. And let's go to the back.
Action.
Action. Okay, so here's the setup. So on the end of the pulley, I've got this cute little 10 gram mass, okay? Then I've got a 20 gram mass, I got a 500 gram mass, and I have the cart. So when I let go of this, oddly enough, it begins to accelerate, right? So what you want to do is you're going to calculate two different accelerations, just like you did with the outward machine. You're going to calculate a theoretical acceleration, you're going to calculate the actual acceleration. So if you're clever, and you all are, what are you going to let the initial velocity of the cart be? Zero. Okay, that'll start from rest. So therefore you don't have to worry about the initial part. So just like with the Atwood machine, what are the two quantities you can measure? Time and distance. Now, I would let this thing travel 50 centimeters, okay? Mainly because you have 50 centimeters, that's 0.5 meters. So if you solve that equation where you have like 2d over t squared, if your distance is 0.5, guess what? You're taking 2 times 0.5, which gets you, so then you're just taking the inverse of t squared, okay? So I don't care which kind of sets of points that you pick. I think I tell you to go from like 15 to 65. It really doesn't make any difference. Just let it travel 50 centimeters, but make sure that it travels 50 centimeters without the weight hitting the ground. So you're going to have it set up like this. You're going to let go, and you're going to let it travel 50 centimeters, and then record that time. And you're going to run 5 trials like that. Then, when you get done with that, then you're going to take the 10 gram mass off of the end, swap that out with the 20 gram mass. Easier said than done. Now, why do I take the 10 gram mass and put that back up here? Yeah, so the total mass remains the same. That's why I take the 10 gram mass and put that up here. Now, look what happens with this acceleration. Okay? So I get a noticeably bigger acceleration. Why?
There's more force applied.
Bigger force, same mass, bigger acceleration. Okay? So there's a direct relationship between force and acceleration as long as you keep the same mass. So then you're going to do 5 trials with that. Now, after you get done with that, let me see that. So you're going to record your times, run 5 trials, take the average. Okay? Y'all know the drill. So you're going to calculate your net force. So that net force, and this is what the asterisk is down below, I say that net force is, we're going to assume that this is a frictionless surface. So the net force is just going to be the weight of what's ever on the end of the string, which is either going to be 0.098 newtons, which we just found up there, or with the 20 grams, it's going to be 0.196. So that's going to be your value. Now, we need the total mass. Well, we've got 10 grams, 20 grams, and 500 grams. That's cool. Okay, we add those together. But at some point, we need to find the mass of this cart. So how can I find the mass of the cart?
A scale.
Weight. But what are our Newton scales going to measure in?
Applied.
No, what units?
Oh, newtons.
They're going to measure in newtons. So how can I take a Newton measure of weight and find the mass of the cart?
It's a,
Acceleration
yeah,
divided by 9.8.
Yeah.
Or something 9.8.
yeah, you just do F equals MA, but make it so that you can find the M.
Yeah, divided by
Yeah.
9.8.
So behind you, hand me one of those.
Yeah.
Thank you. So we're going to turn this on, which helps. We're going to hold it upright. We're going to zero it. And we're going to hook this up And you wanna make sure that this thing is actually kinda hanging, that it's not catching on itself, so maybe something like that. Okay, so this is about 5.08 newtons, okay? So it weighs about 5 newtons. So if this weighs 5 newtons.
But it has the weight attached to it. Does that not
No,
affect it?
When you do this, you want to do this like,
I know, but never mind.
If you hold the string.
yeah,
Yeah, I just
So-
don't know if he did that.
yeah. It's going to be, here's the point, it's going to be about 5 newtons. Okay? I just wanted to show you that it's going to weigh about 5 newtons.
Okay.
So if it weighs about 5 newtons, then how are you going to find the mass?
Divided by negative 9.8.
Yeah, divide that by 9.8 meters per second squared. So if you round it to 10, you got about a 5 Newton cart. And acceleration due to gravity, let's say, is 10. You take 5 divided by about 10, you get about 0.5. So the mass of this is about 0.5 kilograms. You're going to get an exact value, but this is about 0.5. Okay? Then you got another 0.5, 500 grams. And then you got the 10 and you got the 20. So you need to get all of that together, because one of the things you're going to need over here, up there where it's going to say your total accelerated mass, okay, that's going to form the basis of these calculations. So that's what you're going to do. Then you got a bunch of questions to answer. Now, when you get to page 3, what's going to happen is that I'm going to give you a small piece of wood that we're going to put underneath this front edge, like this, okay? It won't be this thick. It's going to be a little bit more shallow than this. But then, and understand the spirit of how I want this done. The spirit of how I want this done is that I want you to, as a group, decide what's going to happen to the acceleration once I put a block underneath here. So look at this in terms of force applied, force opposing, net force, okay? And what's going to happen when you put a block underneath this leading edge, okay? So obviously, if I do this and I let go of it, it actually begins to accelerate backwards. Yours will actually accelerate frontwards, okay? It won't be this steep. Your guys will actually move forward. But what I want you to think through before you, again, understand the spirit of how I wrote this. The spirit of how I wrote this is that you decide, what's going to change? What's going to be different? What's going to stay the same when I put a little block of wood underneath here? Then I want you to run the experiment, do the times. You're going to keep the 20 gram mass out here on the end. I want you to do that, record the times, then you're going to calculate that new acceleration, and then you're going to compare it to what happened. Now, when you get to the back side, okay, when you get to question 10 and all these, it's going to tie in the Atwood machine questions that we had before. If you don't know how to answer number 10, look at how we did the calculations on the front page. The only difference between problem number 10 and what we're going to do on the front page is I changed the numbers, okay? But the thought process is going to be the same. Got the visual about what's going to happen. Okay, stop that. Let's go back up to the front. So what we're going to assume, just like the Atwood machine, the weight that makes it fall is what we're going to call the applied force. Okay? So just this is the same thought process. Oh, the one that has room to fall is going to be the applied force. Okay? Now, what we're going to assume initially on the front page is that there is no opposing force. Okay? There's no friction, nothing. So we're going to assume that my applied force is the net force, because we're assuming that there's nothing working against it going backwards. Okay? Yeah, is gravity pulling it down? Yeah. But guess what? There was a table there to balance that out. Okay? So that's what I want you to think through. So on that first trial with a 10 gram mass, that net force is going to be 0.098 newtons. The 20 gram mass, that's going to be 0.196 newtons. Okay? Because that's the weight of what's being suspended from the end of the pole. You run 5 trials, then you're going to take, to get this theoretical acceleration, you're gonna take that net force divided by the combined mass, that's how you're gonna get a theoretical acceleration. Now, over on page 2, then you're going to calculate the final velocity using your theoretical acceleration and the average time. So you're just going to use v equals v naught plus at, okay? When you get to question number 2, then this is where, on number 2, on page 2, this is where you're going to use that distance equals 1/2 at squared plus v naught time. You're clever, you let the initial velocity go to 0, you're going to know the distance, you're going to know the time, calculate an experimental acceleration. When you get to question number 9 at the bottom, based upon this answers from the previous question, explain why the following statements are incorrect. Okay, so every statement A, B, and C is incorrect. Okay, now let me tell you don't look at statement C and it says, oh, my favorite gravity is 9.8 meters per second squared. Don't get nitpicky and go, oh, that should be negative. That's what makes it wrong. No, okay, it has nothing to do with sign. Okay, it has, your answer to 9C has nothing to do with sign. And don't tell me, well, it's 1.6 on the moon. No, that's not what makes it false either. Okay, it's not what makes it false. Anyway, other than that, you're on your own. So you got about 25 minutes. Let's go do science. Ready, break.